Thank you, and good afternoon, everybody, and very warmly welcome to our panel, Algorithm to Advantage. And my name is Outi Keski-Äijö, coming from Business Finland. Business Finland is the state-owned innovation funding organization that is doing also the international services for the research and the industry, especially for the smaller startups. And we are here now this time with minister-led delegation and happy to be here. In addition, the Business Finland is promoting the investments and also the organizing different type of the ecosystem activities for the companies. In today's panel, we delve into the topics of reaching quantum advantage. And now we are not anymore talking about that if there will be advantage, but more that when and how this advantage will realize. This panel aims to really bridge the gap between the theory and practice. What kind of the practical steps need to be taken to reach the advantage, quantum advantage, and what it means, and how we get from this promising algorithm to the really world-class advantage and the applications that are useful for the industry. And so we had first introductions, but maybe a little bit more also the background, everybody is bringing something with that as well. So Jouni, you in addition that you have now role in the IQM Quantum Computers, you have had long tenure in the Finnish military services. So, then Hannu, you have had long career, more than 25 years in the R&D leadership position in Nokia, and latest one, you had been the CTO in the Nokia technology and responsible for the Nokia's industry-leading patent portfolio. And Valterri, in addition that you are also the working in the and co-founder in the Quanscient, you are also working in Helsinki University as a research fellow in the group of the excellence in quantum computing. And then Richard, you have earlier had also the startup and make the founder of the quantum stream at Creative Destruction Lab. And you have still quite recently graduated from Stanford, so many things done already. So, but now I ask you to just warm up and pitch, your companies, that why your companies are existing and what you are aiming at in a longer term, not just in few years' time, but what is your final target with your companies. Please, Jouni.
Yeah, thank you. So IQM Quantum Computers exist so that we can build and deploy world-leading quantum computers. And why we do that is, of course, that we want to enable our customers and partners at the end users to experiment with quantum computers, because that's how we go towards the quantum advantage, that people have actually access to the actual hardware. And our roadmap goes obviously to 1 million qubits and towards the practical advantage. And that's the purpose of the company.
So QMill is a quantum algorithm company, and we aim to be a leading provider of the quantum advantage in the future. And actually we want to be that very quickly as well. And so in QMill we offer near-term practical benefits of using quantum computing for industrial applications. And We provide a software as a service platform, and we use our proprietary quantum algorithms in that platform. We are currently still in R&D phase, and we plan to roll out our product in early 26. We are headquartered in Espoo in Finland.
Yeah, and Quanscient. So we want to make prototyping entirely digital. That's the visionary statement. And so what do? We do multiphysics simulation software, and we do that both with cloud computing and quantum computing for your engineering R&D type of physics simulations. And we already have a product out there called Quanscient AllSolve, and that's still purely cloud-based, massively parallel physics simulation software. And that we are already shipping to our customers. Now, from the very beginning of the company, since 2021, when we were founded in Tampere, Finland, we've been also developing quantum algorithms for these similar types of simulations, in particular for fluid dynamics problems, because that sort of unlocks the intractable problems in, for example, aerospace engineering and whatnot. So, yeah, that's why we exist.
Haiqu is a quantum software company, and we are building a development environment, an SDK, for users to build applications systematically. And by systematically, I mean applications that combine algorithmic primitives like data loading and techniques like mitigation, circuit compression, other performance-enabling techniques to run, more complex execution flows on real hardware. We're really trying to build the place to run frontier applications across any hardware modality.
Okay, and I know that you have some, Valterri and Richard, you have some common history already, so could you a little bit tell about that?
Yeah, well, they make amazing quantum lattice Boltzmann algorithms for physics simulations, and those algorithms are already quite efficient relative to alternative approaches, but we look at current and coming devices and their constraints, and we understand, okay, how can we exploit the structure within these algorithms to run them more effectively on these devices? So they provide the algorithms and we provide the execution software.
Then when we talk about quantum advantage, I think that is always a different thing for everybody. There is not really somehow common accepted the definition. So I would like to ask you that how do you, each one, think about it? Maybe if you agree that what somebody is saying, then it's fine, but if Jouni, you could start.
Yeah, I would maybe keep it kind of simple. So quantum advantage is something where quantum computers actually outperform the classical computers in some practical real-life problems. And of course, it's in a way relative because high-performance computing is developing all the time, so the target is kind of moving, but kind of very simple definition. But I'd like to add that it's not just the magical, miraculous machine that we develop, but also how people can use it and what are the algorithms and how the industry is able to apply these. And this is something that we need to keep in mind when going towards the quantum advantage and enabling the end users to develop their skills.
So it's time dependent. What is the?
Yeah, and it will be gradual.
Okay.
It's not black and white.
Hannu.
I've been very long time in the industry, and I'm a very practical guy, and I actually agree with Jouni, so that the quantum advantage is reached when a useful mathematical problem is solved faster by using a quantum computer than by using a classical computer. And useful problem means that it has some practical application. And you need a powerful machine in order to do that, but you also need the right kind of algorithms to do that.
Yeah, but what can be the advantage today, maybe not tomorrow or after 1 year. So there is also because both sides proceed quite quickly. And
we will achieve the quantum advantage piecewise. First in some narrow areas and then in some other areas and then ultimately in very broadly.
Okay.
Yeah, I mean, cannot disagree at all.
Yeah.
But yeah, maybe from more of like Quanscience perspective, I mean, for us, we see that quantum advantage is when we actually solve a useful, meaningful physics problem with quantum computers that actually provides also business value for our customers. And how that happens is that, okay, either the problem is intractable to classical HPC at the given time, or that we just solve it significantly faster. But yeah, there's the practical business value aspect that I think is very important as well.
I agree with all the practical statements. I don't think I can add to that. I would just say that, our view is that quantum advantage is not miraculously found by finding the right algorithm and running it on hardware, but it has to be systematically developed by a combination of all the respective enabling parts. So you need to have sufficiently expressible data embeddings connected to, sufficiently optimized algorithms on sufficiently good hardware, et cetera. And so I would say it's built. Quantum advantage is built, and you need to build it sooner than, I would say, start today and expect it in a year.
Yeah, and maybe small addition. So usually we talk about like the time to solution. So quantum computers are faster, but actually quantum advantage can be achieved also from energy to solution. So we can save energy in some computational problems, even though it might not be faster in that case.
What about because I think that the investors now, they are really looking forward, they are craving for the quantum advantage and getting somewhere, next level with the quantum computing. So what do you think that when the patience will end and we might get another the quantum winter, or what is your expectations that what investors are currently expecting?
Well, can I start? So I'm not so much afraid of the quantum winter because I'm quite confident that we can actually achieve the quantum advantage. But I personally think that achieving the quantum advantage is the most important thing for this entire industry. And I think that gaining like a small improvements and small enhancements, it's when I hear them, they are nice applications, but the results are a little bit disappointing to me. But when we start like clearly outperforming in certain problems, classical computers by a factor of 50% or then by a factor of 10 and 1,000 and so on and so forth, I think we are all much better off at that point. There's much more business for computers, algorithms, physics modeling, and software when that happens. So it's quite important. And at QMill, we actually, that's our main goal to achieve the advantage. It's even more important than having some particular applications in some area. And we intend to achieve that advantage next year by 2026, or at latest 2027, when you have good enough machines that make not so many errors. Yeah.
What about Atos? Jouni, what is your plan and schedule?
Yeah, so at the moment for IQM, there is no winter, but the temperature is kind of hot. We just closed the Series B, 320 million USD, so.
Congratulations.
Thank you. No signs of like quantum winter at short term. But of course, we need to deliver on the promises and keep on like delivering on the roadmap and working together with the algorithm companies and showing some progress all the time.
Yeah, I think that there's a lot of optimism right now, and I think the investors understand that quantum advantage is coming, and that when that happens, it will be a huge multiplier for any company's valuation. So I don't think they're afraid or anything like that. Now, as for Quanscience timeline for reaching quantum advantage, it's quite obvious that quantum CFD is kind of one of the more difficult problems, and will require, the exponential benefits of that, the full universal benefits of that will require kind of levels of fault tolerance for sure. But then again, given the roadmaps of the hardware companies, it's not that far off anymore, either the fault tolerance. And we do believe that already in the NISQ era, we do see the first advantages also in physics simulations and computational fluid dynamics simulations. So how we foresee that happening, the first advantages is that you will be able to solve a short simulation of some time steps that is already like intractable in size of the problem to classical HPC. And what you can do there is that you can, for example, use that to train, for example, foundational physics AI models to teach them something about the problem that is just not possible with any classical methods. So that might be the first advantages in quantum CFD. What do you think?
I think we can speed it up, and I agree. Yeah, I think, so we've raised 2 good rounds. We're going to announce the second one soon. It is a highly, when you go to raise money, it's non-trivial and it's highly polarized, and I would say the vast majority of investors are not willing or do not passively understand quantum computing and are generally quite scared, not just because it doesn't work or it's not generating recurring commercial value, but because there's a modality risk from their perspective. There's many different types of quantum computers. What does that mean? So there's a lot of variance across the stack about what might win. You really need to find this restricted set of investors who are really technically capable and very forward-thinking. You can find those, and they are very pro-quantum, and it's very easy to get money from them, but it is difficult to find the right people. I would say that generalist investors at this point are not very involved in quantum computing, and I think will miss the biggest multiples, but that's their loss. What can you do? I think there's a lot of very strong firms that will make their name with quantum computing. So I would say, yeah, if you're a founder, go raise money. It's a good time to raise money. It just won't be easy, but you can do it.
Then, Jouni, you are basically the full stack company, and so why you still? But I would think that still the processor side and the quantum qubit design and fabrication it's kind of like heart of your company, but you still work also for the applications, and what is the reason for that?
Yeah, so indeed our unique ability is to build the machines starting from the processors and actually designing the tools to design the processors, and then like integrating the whole machines, and we do that for our customers mostly to enable their experimentation and building their expertise. But then on the other hand, we want to maximize the value to our customers, so we develop the use cases together with them, and we develop some like algorithm libraries for the customers to use. Because in the end, like the computing users, they are not interested in the machines maybe as such, but the actual useful applications. So we need to help them get there also in-house. But then in addition, we work, of course, with partners to develop the use cases, so it's not all in-house.
What about, what are the really requirements from the algorithm company's point of view, that what do you need from hardware to achieve the advantage?
Well, in QMill, we really focus on using NISQs because we want to achieve this advantage and practical use as soon as possible. For us, it's really important that we have low error rates. So we'd like to have like 4 nines of fidelities from the quantum gates. And we focus on like the size of circuits, which could be like 10,000 gate operations. And we know that's going to be available quite soon. So that's number one thing. The second thing is that we need this hardware infrastructure to be available for us and for our customers broadly. Like we need different types of machines, and we need a lot of this capacity. So we need you to sell more quantum computers.
Happy to do that.
Yeah.
What about Valterri? How do you see?
Yeah, absolutely. Like, I think that incremental, continuous improvements will get us there, and so obviously we need more qubits, we need better fidelities, we need to have more of those nines, as you said. We need to have better connectivities and so on. But we are seeing these advancements all the time, and this will happen. And we trust that our partners like IQM can make that happen. But what we also need is, of course, then the middleware stack. So we really need partners, and we rely on our partners to kind of do the error suppression and error mitigation and all these tools that, for example, Richard is developing for us. So that we can then focus on what we do best and develop the algorithms for the applications and deliver value to our customers as quick as possible.
Yeah. We think it's best to look at it from a ground-up approach. So of course you need sufficiently good fidelities on hardware, and you need to support features like mid-circuit measurements at a higher fidelity. But then software, you want to figure out approximate techniques for running things effectively or suppressing noise. And then once you can define the constraints, so once you know, okay, well I can take a circuit with this level of connectivity and compress it by this degree, then you identify the operable region for an algorithm that would have to find advantage. So, one example in context is we're running right now LR QAOA optimization algorithms of more than 100 layers on more than 100 qubits, which is more than people think you can run. And we can do that by very serious compression, but we can't do it for any optimization problem, especially if one is highly, very densely connected. So you need to identify for example, a more sparsely connected graph or more sparsely connected algorithm, and then figure out what execution technique you can apply to it. So I would say it's ground up, and eventually you land at the algorithm and you try and massage it with the underlying techniques. And that's why like a very direct relationship between all the players in the value chain is necessary to hit advantage in the near term. We love working with Quanscient.
Okay, so as noise is the biggest problem in NISQ era system, but what kind of the applications would tolerate the noise the best? What could be the first ones in that point?
Do you want to start?
Well, noise, it is the worst problem of all at the moment, and we can try to suppress that and mitigate with the errors, but ultimately we just need the noise level to go much down. Then there might be some applications like generating random numbers or sampling random circuits that are less affected by noise.
Yeah, I would say there's some like interesting techniques that are a bit more resilient to noise, like sample-based diagonalization on quantum computers, very hot right now. More heuristic approaches, we expect to find some incremental advantage. We see it empirically with the QAOA stuff. I don't expect anything that requires chemical precision to be advantageous on noisy hardware. And I would also like to add that, we think of hardware as going from noisy to error corrected, but it's a false dichotomy because you really just go to a meta version of what we currently have, which is partially corrected noisy logical hardware, and pretty much all the same constraints apply. So I think initially it's these more heuristic algorithms that will find some benefit. And I think CFD is actually quite promising in the near term based on Valtteri's algorithms scalings, but you probably have to find some ways to make certain things more noise robust.
Yeah, and some of the ways that we're looking into is, for example, okay, this gets a bit technical, but these quantum lattice Boltzmann, quantum lattice gas automata hybrids. So in this lattice gas automata type of methods, you kind of deal with sort of individual hypothetical particles, and then you do a lot of ensemble averaging. So this ensemble averaging actually can consume some of the noise. So this can be quite resilient for that.
Okay, so there is some techniques and algorithms that you tolerate that better.
Sure.
Okay.
Can I ask from Jouni that how do you then plan to reduce the noise? What is the roadmap for that?
Yeah, of course, we have very ambitious roadmap also to reduce the error levels first in NISQ devices and then quantum error correction demonstrators first and then towards logical qubits. So we will get there. That is, of course, as important as increasing the qubit count, if not even more important.
Agreed.
Okay, then I think there has been recently a lot of talk about going directly to the not kind of like trying to achieve the advantage in NISQ era, but going directly to the fault-tolerant machines and so on. But I understand that you all are now working for the NISQ era. So why? Because I think that it is also more difficult to find the proper or identify the correct ways or correct advantage areas, or it might not bring as a such advantage yet. That would be really kind of like having a lot of business value. So why you are doing that?
Do you want me to comment on that? Okay. So I think, well, first of all, I think that ultimately in quantum computing, just like almost in any other area of technology, it is the applications that will have most of the value, then and the value will be for the end users. And in this case, it's about creating applications by using algorithms. And we think that this advantage can be achieved already in the NISQ era, but on the other hand, this fault-tolerant area is not that far away, because companies are road mapping hundreds or even thousands of logical qubits in a matter of 3 to 5 years. So it's not that far away, and therefore now is the time to start investing in software and in the algorithms. And we need those in order to bring those practical benefits for the end users and for the industries. So start investing in algorithms. It's the right time to do that now.
Yeah, I fully agree. Yeah. And also, I mean, developing applications for the NISQ era already, I mean, that gives direct feedback to the hardware providers as well. Okay, like what do we still need? What do you still need to do to reach that advantage? And I think we all agree that during the NISQ era we'll get that advantage. And at the same time we are developing, because we are developing NISQ applications, it means that we are also developing these error suppression techniques, error mitigation techniques that are a necessary stepping stone to the fault tolerance anyway. So I mean, it would be only stupid not to develop applications already now.
I think it's really nuanced, and we don't categorize it into two eras generally, or like it's important to consider the early fault-tolerant era as a clear graduation from NISQ, because it's still a noisy system. You still have the same operational constraints. It is, from the user's perspective, just a further abstraction. So you're working on a logical gate set versus a native gate set, but it's still noisy. And I think there's even cases where, let's say we think quantum machine learning is very cool. We think it could be a dark horse application-wise. There may be cases where you don't even want to apply coding schemes. You might prefer to apply things like passive, let's call them decoherent free subspaces, to learn in, where you're not actively coding and pumping out errors, but you're more so learning in resilient, error-resilient subspaces. It comes down to the operational bandwidth of the device, but we don't think it's going to be as simple as an immediate shift to fault tolerance. It's going to be application-specific. There might even be algorithmic-specific coding that people do. So picking the error correction code based on the nature of the algorithm. So I think it gets really complicated, and people need to start thinking about the transition now and paying for all of our products.
Yeah, so Richard, still to you, because I mean now you are working with this middleware layer, and they're doing different error suppression and mitigation and all that, and also you are helping to kind of like run the application in different hardware. So kind of like, how do you, I mean, is that one, or how do you would describe that is also one way to ease companies' way to find the correct hardware for their problems?
Yeah, I think the nice thing about it is it's not too complicated. For example, if you have, let's say, a chemical simulation with a really high requirement for precision, and it's non-variational, so you only need to do one really nice run, and it's densely connected. Maybe you prefer a device with all-to-all connectivity that's more stable, albeit very slow. If you have anything with a variational demand, then you very obviously have to go to a faster high-fidelity device, like a superconducting device, and eventually a photonic device. So I think there are macro parameters that clearly delineate you. And then, okay, it can get more nuanced, and we're also seeing a lot of competition on problems that we thought would have been obvious on one modality between different ones. And there's also ways to take a variational problem and map it to for example, a trotterized evolution, and suddenly it's non-variational. So it does get complicated. Basically, you need to try it. You need to try a few different mappings on a few different devices and progress empirically.
Yeah, Hannu, last words.
Can I say one more thing, even though we are out of time? So why is it important to look at applications now? Just like in any industry, in this industry, we need to listen to the customer. We don't want to just push some technology to the market, but we need to understand what the customers need. We've been looking into the computing market, and almost all industries do computing, simulations, optimization, whatnot. In some of those, there's a great demand for faster computation. In some of them, there are not. We need to understand where the real need is. And then we would apply quantum computing in those areas.
Yes, and make that really useful and kind of like get to the next level, that we are more commercialized customers and not just this kind of like research word business, what we are currently doing. So thank you for your all insights to this, and thank for the audience. And I hope that we can continue the discussion outside of this room and space. Thank you.
Thank you.
Thank you.